Log on, tune in, find out. Another good idea from Cambridge.
Okay, so thank you for being here. This talk may be the most surprising part of the talk is this word here, new, because my talk will consist of two parts. Part of it will be on linear PDEs, and part will be on a particular class of nonlinear PDEs called integrable. And the surprise here is that this new refers to both parts. And you see, our early speaker was from the great institution of Caltech, and I was there a graduate student. And a lot of what I will present today has its origin when I was a graduate student. So in some sense, there is this connection. So new transform, this is very strange, you see, because when we talk about classical transforms, we think about Fourier, Laplace, etc. So is there really anything new after these classic words? And the surprising statement is that the answer is yes. And when we first came up with this idea, it was difficult really to convince first ourselves and then the public that there's something new. But by now I think it's we can certainly say that this is the case. So the talk will consist essentially of three parts. The first part, I will motivate the introduction of this new procedure, and you will see that something strange happens, namely usually we go from linear to nonlinear, and in this case the process was the opposite. So we went from nonlinear to linear. So the second part is we'll illustrate this new transfer for linear PDEs, and then the third part will go back to nonlinear problems where actually this method really originated. So this is the plan of the talk. So the motivation is the following. There exists a distinguished class of nonlinear PDEs called integrable. And I don't want to explain what integrable means. I will just only emphasize what is the essence of integrability. And the essence of integrability is the following. So here is a typical equation which is integrable, which is the so-called nonlinear Schrödinger equation. By the way, I should point out that integrable equations are very, very, very limited class. On the other hand, they are physical. There's a very nice article by Francesco Calogero that explains why these equations are both in some sense integrable and appear so much in applications. But here is a typical one, the nonlinear Schrödinger equation. So what makes this equation distinguished, or in my language, integrable? What makes it distinguished is the relationship of this nonlinear equation with a pair of linear eigenvalue problems. So for a moment, please forget about this nonlinear equation, and let's concentrate on these two linear eigenvalue equations where your eigenfunction is m and your eigenvalue is the complex variable k. Sigma 3 is the third Pauli matrix, and Q is this. Okay, so what is interesting here? What is interesting is the following. You see, suppose that you are given this function Q, which is a function of x and t. Yes? Then it's clear that if I give you Q, in principle you can find m, but the count is wrong because you have two equations that m must satisfy. Yes? So already you see that this pair of equations will not have a solution unless some miracle happens. Yes? Namely, they should be compatible, and this compatibility condition is precisely the statement that Q satisfies the nonlinear Schrödinger equation. And once you make this connection, once you realize that this nonlinear equation is equivalent to the compatibility condition of these two linear equations, you might ask the following question. You say, well, I now have this connection. These equations are linear. This equation is nonlinear. So maybe I can obtain information about this nonlinear equation by analyzing these linear equations. And this is correct. And the first important result was the possibility, or actually the fact, that you can solve the Cauchy problem on the line for this equation. So what you do to solve the Cauchy problem for the line? You see that if you don't have this nonlinear term and you have some nice initial conditions, how nice? So nice that your Fourier transform will work, then the answer would be obvious. Yes, you would just use it by solved by Fourier transform. So what do you do now? What you do now is you ignore this equation and you analyze this equation in such a way that out of this analysis, or mathematically out of the spectral analysis of this equation, you find a nonlinear now Fourier transform. And then you use this second equation to find the evolution of your nonlinear data. And this is the procedure that allows you to solve this equation. Now, of course, you have some subtleties, namely, in terms of everything being closed form is not anymore. But conceptually, this is what happens. So this was well understood, and several equations were solved this way. So in the early 80s, the question was, okay, suppose that this equation is not posed on the infinite line, but suppose it's posed on the half line. Suppose you have boundary conditions. Is it possible to still do something about this? You see? And people worked on this problem for many years, and I did also, with no results. Finally, in 1997, after about 15 years working on this problem, there was progress, and the progress was surprising. Namely, the new understanding was the following. I mentioned earlier that when you solve the Cauchy problem on the line for this equation, you only analyze this equation. You see? The new understanding was that if you want to analyze boundary value problems, then what you should do is be more democratic and analyze these equations simultaneously. And it was the first time that spectral analysis for a pair of equations was done. You see, unless you have this compatibility, you cannot even pose this problem. Because as I mentioned earlier, come on. As I mentioned earlier, these equations in general will not be even compatible. Okay? So this was if you want, the breakthrough, the conceptual breakthrough, that you should perform simultaneous spectral analysis of both equations. Okay. But then, in terms of linear equations, the surprise was the following. Now, you solve the nonlinear Schrödinger equation, and you obtain some formula, right? If you do the Cauchy problem, when you look at the linear limit of this formula, of course, what you find is the formula you will get for the linear part if you solve it by the Fourier transform. What will happen if you take the linear limit of the formula you got for the boundary value problem on the half line? And thus I was surprised, because you got something which is not classical. Okay? And then you realize that what you have then, therefore, this way is you have solved, if you want, the analogous boundary value problem for the linear equation by some new way, some new way, and this led to the Fourier to the introduction of a new method for linear equations. Earlier on, there was an important development, because I was very fortunate that the late Israel Gelfand visited me, and he wanted to understand deeper what it means that you solve a nonlinear equation by this new way. You see, Gelfand, when he first posed this question to me, I thought he was teasing me, because he told me he didn't understand anything, you know, and he had played an important role in the solution. But it turned out, of course, that different people mean different things by understanding, and Gelfand always wanted to understand something very deeply. So through his insistence we realize something that the classics should have realized, but somehow they didn't. Maybe they didn't have a reason to do it. And what was the realization is that, of course, linear equations also have Lax pairs. Yes? And here is a Lax pair for this equation. So what's the statement now? The statement is that this equation is the compatibility condition of these two pair of equations. This is so simple, mu now scalar. While you're watching me, you can do it. If you take a t derivative here and an x derivative here, and you eliminate mu xt, you will find that vu satisfies this equation. Okay, and now let me make a statement. You see, I told you earlier that I cannot explain to you what integrable equations are, but now maybe I can make a statement about what integrability is. And what integrability is the expression of a deeper kind of separability, which is valid for nonlinear PDEs. You see? So if you have a linear PDE like this, you can separate variables. Okay? And you associate this linear PDE with two ODs. But this is by no means a statement of equivalence. Yes? By no means this equation is equivalent to those two equations. Yes? On the other hand, the statement is that this equation is absolutely equivalent to those two equations. So this kind of separability statement is deeper even for linear PDEs. But of course, its advantage is that it non-linearizes. So does this new understanding for linear equations give you anything new? Well, now you see, if you want to derive the Fourier transform, if you separate variables, you do it by the spectral analysis of this equation. My suggestion is, of course, you can also derive the Fourier transform by doing the spectral analysis of this equation. And it's indeed the nonlinear analog of this that gives rise to the nonlinear Fourier transform needed for the nonlinear equations. Well, therefore, you have a new way of deriving transforms. And the first time that this became clear that it's powerful is through the work of Roman Novikov, who generalized some earlier work, some earlier joint work, where he inverted the so-called attenuated Radon transform using this technique. I will not talk about this today, I will talk about this tomorrow. And this is really very important in medical imaging, and we have a joint paper with Arya where we numerically implemented this. You see? But in terms of boundary value problems, this new understanding, as I mentioned at introduction, gave rise to a new way of solving boundary value problems. And originally, I was doing this by the simultaneous analysis of the Lax pair, but of course later it was realized that you can do it directly without ever having to talk about Lax pairs, in spite of the fact that this was first the motivation. So now, what I'm going to do is I'm going to do a couple of examples where I use this new approach to solve linear equations. Yes? And in order to emphasize the power of this method, I will start with the most classic of all classic problems of the with the heat equation. You see? So the question is, can you say anything new about the heat equation? And of course, if somebody had asked me this question a few years ago, I say it's crazy. How can you do anything better than Fourier? But the answer is you can. Okay, so here's the formula, and then you can decide if it's better or not. Yes. So here is the formula. So let's solve the easiest of all easy problems. Okay. So we take the heat equation, but now we do it. You see, if we do it on the full line, then you have the Fourier transform, and you cannot do better. You see? But suppose you do it on the half line. You do it on the half line, and let's take, for simplicity, the Dirichlet problem on the half line. Okay? Then, if you open any book, you will give you this answer. Okay? Will give you this answer. Okay, is this good? Well, first of all, it's a solution, which means whoever, and there it's a solution. But once you begin scrutinizing this, you find different unpleasant facts. And these unpleasant facts have nothing to do with this equation, are typical of problems solved by separation of variables. As my former student Ewan Spence has written a very nice paper explaining all this. I don't see him here. I know he's here. Okay. So they have all these unpleasant features. So what is the unpleasant feature? Okay. You see, and this is, for me, something very strange. This formula is almost in every, not almost, in every book written on transforms in applied mathematics. Nowhere in this book, in these books, I have seen the proof that this solves the heat equation. Okay? I mean, I remember, again, you see, Gelfand, for other reasons, asked me to solve this equation, and I did, and I derived this formula. You see? And after I did, he told me, he asked me, are you done? I said, of course, I'm done. This is the formula. He said, you have done nothing. And of course, he was right. Because what do you mean you have done nothing? Because in order to derive this formula, you start with the heat equation, you take the transform, so already you assume that the solution exists. How do you know the solution exists? You don't even know anything. If you have a priori statements about existence, you can do it. But if you're going to do everything by first hand, then the only way to do it is to say that God or Allah, whatever you believe, gave me this formula, never mind how I derive it. But now everything here is well defined, so I can prove everything rigorously. Yes, because this is the sign transform of initial conditions which you have, so you control this function. This is the time transform of your boundary value, so of course you control this function. Therefore, you control this integral. So now you can prove anything you want with this. Yes. So for example, you can prove that this satisfies the heat equation. That's trivial. Let's don't do it. Number two, you should prove that when t is 0, this satisfies your initial conditions. Again, it's trivial because when t equals 0, this goes out, and now you can appeal to the inverse sign transform. But then, the last thing you should do, and as I said, I have never seen this done in any books, is you should prove that when x equals 0, this recovers this. Yes? But as soon as you do that, then you see, of course, you can do it if you work, but it's not trivial. Why it's not trivial? Because if I put here x equals 0, and naively I put it in, this vanishes. Yes? What does it mean? It means, you see, that this integral is not uniformly convergent. And as I said, this has nothing to do with this particular problem. It's true for any problem solved through separation of variables. Okay? And people that do numerics, of course, they know that this is also, that's why nobody uses this to compute anything. Okay? So, by the way, I was at Caltech when first somebody asked me this question, you see, as a student. And you see, what do you do? What do you do when somebody tells you, how do you deal with this lack of your use? Well, you tell them go to the complex plane. Yes? And indeed, that's what I have done here. So now that I have given some bad publicity for this classical solution, let's go to the new solution. The claim is that this is the good solution. Okay? So what does it involve? You see, this part is the defined here is the Fourier transform of your initial condition, right? And this function is the t transform of your boundary values up to capital T, which is where I solved my problem. So this is well known, and this contour is this. Now this solution has not this problem of uniform convergence or anything. After all, later on I will show you that you can compute effectively this formula. Okay, so this already is a surprise because it tells you that for the heat equation you can do something better, but actually the problem that gave rise to all this was the next one, which is the Stokes equation. For people that do water waves, they know that this equation has a lot of significance because actually you see when Russell found the solitons for what later became the KdV equation, you see he challenged the great people of the time to explain to him this phenomenon. And there were two great people, Stokes and Airy, you see. And they both claim that he was crazy because they both make mistakes. You see, Stokes derived this equation as a limit, which of course doesn't support solitons. And Airy derived the complementary, so he didn't keep this term. Okay. So this is Stokes' equation. So now, suppose you want again to solve this equation on the half line. Okay, so when your first instinct is to try to use I have to go faster, though. I'm not going to do anything. You see, your first instinct is to use an X transform, right? So what is the analog, if you want, of the sine transform or the cosine transform for a third order problem? You see, the answer is, if you look at the book, if you look in books, like any book, there are not any, you cannot find any, then you prove by first principles that such transform does not exist. Okay? There is no an X transform to solve a third order problem. All right, then what you do? How do you solve this stupid problem? I mean, well, you say, I do Laplace transform, yes, in t. But you have an evolution equation, you go from 0 to finite t. Why should I go to infinity? Furthermore, even here, I will have to invert a cubic in order to do Laplace transform, you see. This, by the way, when I decided to leave mathematics and go to medical school. I couldn't do this problem. I couldn't do this problem in any reasonable way, okay? But finally, we can, of course, now, and this is the answer, you see. The answer is as beautiful as before. Again, you have this I defined in the earlier transparency. This was the Fourier transform of initial condition. This now is a little bit more complicated, but it's explicit, of course. So it involves what? Remember, before we had the Fourier transform at minus k. Now this involves the Fourier transform at the two roots, the two transformations which leave the dispersion relation invariant, and this was defined before. So this absolutely explicit formula I will give, and the contour is this boundary. Okay, so let me give you a hint how this formula can be derived. I'll go a little bit faster now. So this is this, and how can this formula be derived? You see, let's go back to the heat equation. You see, this method does the following. First of all, it gives an integral representation of the solution. In this integral representation, just like your Green's representation, involves all boundary values. But as a matter of fact, it involves, as you see, transforms of boundary values. Yes. So if you do the heat equation, it will involve not only the transform of the Dirichlet-Dater, but also the transform of the Neumann-Dater. So this is the first thing you get. Okay. It's not effective yet. Why it's not effective? Because you don't know this function. Yes? But please note that you never see in this method boundary values themselves. You only see their Fourier transforms, or your spectral data, if you want. Then, what is the second key ingredient of the method? The second key ingredient of the method is that all transforms are related by some equation which I call the global relation. And this is the equation. Okay? And then what you do is by algebra, simply by algebra, you eliminate what you don't have. By algebra. You never have to invert anything. So in this case, you see, this you know, this you know, this you don't know, but it will play no role because you don't expect the solution to be affected by future time due to causality. And you get this equation to replace this in terms of what you know. This drops out, and that's how you get the previous formula. Just very quickly, what happens in a third order problem? You see, the third order problem is much worse because now you will have two unknowns. Because since I gave you the Dirichlet-Dater, the first derivative is unknown and the second derivative is unknown. And if you go to an equation with 20 derivatives, you will have about 10 unknowns. Yes? And the statement is there's no other information. All information you have is this. There's no more. So how are you going to solve one equation with 20 unknowns? You see? The answer is the complex plane. Namely, this equation is, you see, when you do the problem on the line, you see, you cannot move off the axis, you see, but you have no unknowns. Now that you do the problem on the half line, this equation is valid in a huge area. It's valid in the entire lower complex plane. So what you do, you go to this equation and you say, what are the transformations which leave my unknown functions invariant? You remember, these don't depend on k, depend on nu of k, on the dispersion relationship, on omega k. Therefore, any transformation which leaves the dispersion relation invariant, in this case these transformations, will leave unknown invariance. but they will change the equation. So from one equation you will get many. How many? As many as you need to solve the problem. Yes? So in this case, this equation is valid. This equation is valid in the lower half plane. Maybe this died. I think it did. Okay. If this equation is valid in the lower half plane, there was some stick. Ah, very good. This I was doing. Bravo. The stick. Okay. So you see, this equation is valid in the lower half plane. You see, in particular, it's valid here and here. If you use transformations, they mark both these regions here, whereas you want to be. So in this region, you have two equations for two unknowns. So again, by algebra, you get what I had before. Okay. Once you do that, you realize that you can extend this. Yes, this doesn't work, but I can use this now. You can extend this to any equation, but I will skip this. I will skip this, the theory for any equation, because I will not have time to say what I want to say. But just very quickly, what you do is you write the equation in divergence form, and then you have two steps. One step is to write, so if you're doing on the half line, one step is to write the integral representation. You see, it's very general. This applies for any equation. You don't care if it's third, fourth, or anything. The boundary is defined by this formula. And then the second step is somehow you have to use the global relation to eliminate all the unknowns. But again, I emphasize that you don't eliminate unknown boundary values. You eliminate unknown transforms of boundary values. So this is just algebra. Okay. Of course, once you have this, you can prove theorems. If you like to prove theorems, here is such a theorem, and Guillaume has written a very nice paper related to this. Let me go a little bit further, faster, because I have to do some nonlinear problems as well. I promised some numerical statements, and you see, one of the nice things about maybe this approach is its pedagogical aspects. You see, when we teach students, you know, we teach them all these transforms, or depending how rigorously you want to do it, you have a representation, and then when it comes to compute, you say throw it away, it's useless, and then you start again. Yes. So now the claim is you can compute this. So here is an example where I have some initial and boundary conditions for which the transforms can be computed explicitly. Therefore, numerically, to solve the problem, all you have to do is compute a single k integral. Okay? But if you look at this, you can immediately see that just by a slight deformation, if you go, remember originally I was on this contour, you can go to this contour. On this, or on the original contour, I had exponential decay in x, but oscillations in t. Okay? But if I go to this, I have exponential decay in both. So you can do it even by hand. If you choose 5k points, you will get enough accuracy. So this was the work with Natasha Flyer. So anyway, we did another problem because she was interested in this problem. This is the third order problem. So you have some waves emanating. She had done some earlier papers with Fomberg where they couldn't get very nice things, but anyway, you get this in an elementary way. Let me give you perhaps more surprises, which comes from the finite interval, and this was mainly the work of Beatrice Pelloni. When she first told me about this, I was surprised. So I will tell you what the surprise is now. So you see, let's go back to the heat equation. If you go to the heat equation, if you do it from 0 to 1, yes, you have a sum. If you do Dirichlet, you have a sum. Again, the sum has the same problems I mentioned earlier, because of course it's not uniformly converged at the boundaries. Yes, and then, okay, suppose you do a Neumann problem. Then you have cosine sums. But now suppose you do a Robin problem. Okay, then the spectrum is a transcendental. So you have a sum over a transcendental equation. Okay, and then let's suppose you want to go to a third order problem. This is the surprise that Beatrice discovered, and I didn't believe at the beginning. So I just want to do this stupid Stokes equation, yes, from 0 to 1. Can I do it by some formula? The answer is no. I mean, this was the huge surprise. Okay. However, you remember this approach never gives you sums. Yes, it always gives you integrals. So the discrete spectrum is much richer. The continuous spectrum is much richer. So in general, for finite interval, you will get a representation like this. You see, before we had these two terms. You see, if you solve the Cauchy problem, you have only this. The infinite line problem, you have this term. If you have finite, if you do half line, you have this and this. If you have finite interval, you have this and this and this. Okay. By the way, using this formula, you can very easily go to limits from one to the other. Now, remember, when you did half-line problem, roughly you have half the number of unknowns, you see? But remember, this global relation was valid in the lower half plane, so you get a lot of freedom. What happens now? If you do finite interval, you have double the number of unknowns, so the situation appears even worse. However, the global relation now is valid in the entire complex plane. So you have much more freedom for this transformation. So again, you get as many equations as you want to do it. So let me again just give you formulae. So what I'm going to do is I'm giving formula for the problem I said it was hard before. So you see, so please look back. So always it's going to be this form. This is explicit. Yes, these are well-defined contours. So I only have to give you these two functions, and then I'm done. Yes? So I'm going to give you this function and this function. So I give you these two functions for the heat equation on the finite interval, but with these boundary conditions. So Robin on both sides. Yes? Even this I could not find in the book. They usually do Robin on one side. But now look, this is the formula. Everything is explicit, these integrals are well defined, no sums. Okay? So what is the discrete spectrum? What is this spectrum? You see, you have this delta, and this delta has some zeros, and you can see very quickly here that the zeros are on this line. So if you decide, for whatever pathological reasons, to collapse this on here, you will pick up the zeros, and this will give you the sum formula. You see? But note, you will get, if you do that, you will pay two prices. One price is you have a sum, which all the problems of lack of uniform convergence. And number two, the sum will be over a spectrum which is transcendental, because the zeros of these equations, if gamma 1 and gamma 2 are not zero, is not explicit. Okay? Now, the last example before we go to nonlinear things is the third order problem. So in order not to write big formulae, I took, so it's the Stokes equation, some initial condition, one boundary condition on the left, two on the right. This is what makes the problem well posed. Yes? Again, I have to give you explicitly these functions. These are explicit formulae. Okay? So this is the only data is your initial conditions. This is the Fourier transform evaluate at different points. What are the contours? You see, I'm sorry, this is not correct. It should be like this. But anyway, this should have been a bit. I mean, these are the contours in the limit of large infinity. But never mind. Approximately, the contours are these three contours. Okay. Now you ask the question. What about a discrete spectrum? Well, you might think that if you collapse this on the zeros of this, you will get it. This function is given by that, and you can prove that it has zeros on this line, on this line, and on this line. And the statement is, because now, you see, you don't have enough analyticity, you cannot deform these contours to pick up the discrete spectrum. And now, after we suggested this, or after Beatrice suggested this, there are a couple of different mathematicians have given rigorous proofs that indeed this problem cannot be solved by discrete spectrum. Okay? Of course, even if you could, this is much better. Okay? All right, let us make some remarks about elliptic equations, and you see, I want to say something about nonlinear problems, so I will not say much about elliptic problems other than this method in terms of analytical results has given several interesting analytical results. So this work is on the biharmonic equation. This is on the equilateral triangle, and the work of Yu and Spence is on right isosceles triangle, and also on polar coordinates. He has analyzed a classical problem which was again related to Caltech. Don Cohen did a lot about the diffraction. So it's Helmholtz equation outside cylinder, and there are all this interesting history about if you try to do separation of variables, you have one solution which is correct, but it's useless because it's the sum. You cannot do asymptotics. Then you have another solution which is incomplete. It does give you some asymptotics, so it's useful but wrong. So I remember when I took this course by Don Cohen, I wrote a big circle in my notes because you say it's correct but useless, wrong but useful. I mean, this was a very strange statement. And just recently, U.N. Spence was able to redo all this using these new methods. And maybe the more significant of this is the work of a former student of mine, Anthony Ashton. So I had suggested that this new approach, you see, because you work in the Fourier space, should allow you to do rigorous estimates for elliptic problems, avoiding all these complications of singularities, etc. And apparently this indeed has been achieved by Anthony. So in terms of mathematical contributions, up to there are a lot of analytical results for problems that could not be done before. But in terms of long-lasting results, maybe this is the most important. And then you see, in the same way that you can use the boundary integral method in the physical space, you can do the analogous thing in the Fourier space. And this has been done. There's a nice paper in the book which was published by Ari, etc., in this semester, and there is this explained by U.N. Spence. Okay, and finally, maybe in terms of numerics, the most exciting new thing is I saw a paper by Ben Formberg and Flyer where you use this technique to do this classical trapezoid problem numerically, and they claim that they do it better than the classical approach. But just leaving this topic, I want to say two things. One is I'm enormously surprised that you can say something new about such classical problems, number one. And number two, my feeling is that this is very new and there are many things to be done. So for young people, maybe this is a nice area to invest. So let's now go to nonlinear problems where all this started anyway. But maybe some summary before I leave it, just because there are a lot of Cambridge connections on this transparency, and I can try at least to place this new method somewhere. So you see, the first PD was written by D'Alembert, and he immediately understood that you can use separation of variables to find solutions. Euler did it more systematically. Maybe the next big step was by Fourier, when he introduced both Fourier series, were earlier done by Euler actually, and Fourier transforms. Cauchy, of course. And then the Cambridge connection is with Green. You see, as you know, Green was a heroic person. I mean, he didn't come to Cambridge to do mathematics until he was 40. I mean, this is unbelievable, especially in these days when 40 was almost the time you were begin thinking about dying. You see, indeed, he died just a couple of years after he finished. He left his college, and then he introduced what many things. I mean, he had introduced them earlier, but Kelvin found his papers. So in 1845, and Kelvin propagated Green's work. Green's work became known through Kelvin. You see, all these Green identities, etc. And he also introduced the method of images. You see, so what one can say? One can say that, roughly speaking, up to now, to do analytical solutions, there were two different ways of doing it. One was transforms, yes, like Fourier transform, etc. And these transforms have all the limitations that we know. For example, even explain to you a very simple equation, you cannot find the transform. It demands separation of separability, etc. Then there was this more powerful approach of Green, where you have the solution arbitrary domain, arbitrary bound, you have an integral representation in the physical space. But this is more or less useless for analytical considerations. It's useful for estimates. It's useless for analytical considerations because you have unknown boundary values. Yes? In some very special geometries, you have the method of images where you eliminate these unknown boundary values and you get an expression which is the best because it's very simple and has only in terms of what you know. What is the new method? You see, the new method basically what it does is really something like this, but in the Fourier space. So you remember this general representation I gave you was what? Was a representation which had in it all the boundary values, just like green, but it was in the Fourier space. So you never saw boundary values themselves. You saw transforms of boundary values. Yes? What is the advantage? The advantage is because you are not, it turns out that when you are in the Fourier space, you have this idea of invariance is much richer, which was expressed through. So rather than using images, you have the invariance of this global relation, which allows you to do what I showed you earlier. Let's go to nonlinear problems. Okay, so in the last 10 minutes, something about nonlinear, and even there will be a surprise. It's a very recent result. So, so what happens? Well, remember, you have initial conditions, and the initial conditions you define its Fourier transform. Now is some generalization of it, some nonlinear Fourier transform, which I will call gamma. Right? Then you have, I'm doing this only for the Schrödinger equation because I will talk about only the nonlinear Schrödinger. Then you have two, if I do Schrödinger equation of the half line, I have two unknown boundary values, the function and its derivative. And then what I did is I looked at their transforms. Yes? You remember this was a transform of this, and this was a transform of this, and I call this function their collection g hat of k, which appear in my integral representation before I use the global relation to eliminate this. And the analog of that now is what I will call capital C. And the difference is that while this is closed form, this is in terms of a linear Volterra integral equation. Okay, the next step, Q, I wrote an explicit integral representation. Now it will turn out, instead of this, I will have a Riemann-Hilbert problem. So this explicit integral representation at the beginning involved only those two. Indeed, this Riemann-Hilbert problem will be formulated only in terms of these two. Okay. Finally, we had, well, if you want to have an effective formula, you remember I eliminated this in terms of this and this. Yes? I have to do the same. Therefore, I have to write this C of k in terms of gamma and the given boundary conditions. Yes? So this is the analogy. Yes? So I'll give you the formulae, but conceptually, everything is similar. And actually, if I had used this simultaneous spectral analysis to do the linear problem, this would have been even stronger because at this stage, instead of this, I would have obtained a Riemann-Hilbert problem also, but this Riemann-Hilbert problem would have been scalar, and then I could solve it in closed form, while this I cannot. So here are some formulae. So here, for example, so you give me initial conditions, and from this initial condition, I will define this function gamma. Yes, and to define this function gamma, I have to first solve this pair of linear Volterra integral equations. Yes? So you give me Q0, I solve these linear Volterra integral equations, I find phi1 and phi2, I evaluate them when x equals 0, and I find A and B. Note, by the way, that indeed this is some kind of nonlinear Fourier transform. Why? Because suppose that Q0 is small. Yes? If Q0 is small, phi2 is like 1, right? So this now is 1, and then I evaluate to find B, I evaluate at x equals 0, so this becomes the Fourier transform. Yeah? So this is nothing but a nonlinear version of the Fourier transform. Okay? Similarly, you see, if you have both boundary values, of course, for a well-posed problem, you have only one of the two. If you have both, from both boundary values, you solve these Volterra integral equations, you find phi1 and phi2, yes? You evaluate this at capital T here, and you have your A and B, and then this ratio is what I call C, yes? Again, you can very quickly see that if the problem is linear, this term drops out, phi2, you see this term drops out, phi2 becomes 1, yes, and this is what we had in a linear problem, yes, because the linear problem had just this transform of this from 0 to capital T. Yeah. So this is indeed, now in terms of the integral representation, you have, as I told you, the solution of a Riemann-Hilbert problem. So what is a Riemann-Hilbert problem? So for Riemann-Hilbert problem, you need a contour. So this is the contour. You see, when you do the problem on the infinite line, your jump is along the real axis only. Now it's slightly more complicated. It has jumps both on real and imaginary axis. There's an easy explanation. I don't have time. So a Riemann-Hilbert problem means what? I have to give you a contour, which is this. And on this contour, I have to give you certain jumps. So what I'm trying to do, I'm trying to find a function which is analytic everywhere, including infinity, except it has some jumps when you go across there. Of course, it must have some jumps, because it's analytic everywhere, including infinity, it would be trivial, yes? So the only reason that this analytic function is not trivial is precisely because of these jumps. So if I give you these jumps, in principle, you should be able to reconstruct this function. So what are the jumps? The jumps are uniquely defined in terms of what I told you earlier. So remember, earlier we had this gamma. I also had this A. So from this, I define the little gamma, which is here, right? And then I find C, which remember was the ratio I had before. From this I define capital gamma. So my jump matrices are explicitly given in terms of this spectral data. Right? Now I have these jumps. Question, is this Riemann-Hilbert problem well defined? Does it have a unique solution? The answer is, it turns out, because they have, you see, this is the Hermitian of this, because of these symmetries. There's an old theorem of Krein. You can prove that this Riemann problem has a unique solution. So you find M by solving it. Once you find M, and yesterday, if you were here at the talk of the young Olver, he spoke about ways to do some Riemann problems numerically. So if you find this M, then you put it here, and you find Q. Okay? Again, this is nothing but the nonlinear analog of the formula I would have obtained if, instead of the heat equation, I was doing the linear version of this. Because look, in the linear limit, this term will drop out, of course. Yes. In the linear limit, this will become 1. And this, remember, was the Fourier transform of initial conditions in the linear limit. So this will be the first term of my representation. This will be 1, and this, remember, was the combination of the two terms, and the contour is exactly what would have been. Okay. So this is precisely the nonlinear analog. But as I said, what happened here is this formula was obtained first, and then the linear formula. Okay, but remember, there's a problem here. What is the problem? At this stage, we have to eliminate the unknown part of the spectral functions. Yes. Because remember, in order to compute this capital gamma, I need both Dirichlet and Neumann data. So I have only half of them. So still this formula is not effective. Okay. But there is still, I have a theorem. You see, you remember I criticized for not showing in the linear problem that this is a solution. Can we show that this is a solution of the nonlinear problem? And the answer is yes, you can do it, you see. And what you have to say is, again, what you do is, from initial condition, you find this function. Okay? But I give you two functions, let's say, G0 and G1, which are the boundary values. They are not independent. Yes? Remember, they are coupled by the global relation. The theorem is, if these functions are such that the global relation is valid, then indeed, if you evaluate this at x equals 0, you find this, and if you take the derivative, you find this. There is a particular class of boundary conditions for which you can eliminate very effectively. So for a particular class of boundary conditions called linearizable, you can eliminate, you can indeed express C in terms of the nonlinear Fourier transform of initial conditions and your boundary data. So this is, for this class, everything is effective, but even without this, you can still do asymptotics. You see here, for example, some glorious formula which is complicated, but all wants to say is that, you see, in this business of integrable systems, as you saw, a lot of things are not explicit, so you say, what is the use of it? So there are many uses. One of them is, still remains the only way to do effective asymptotics, you see? So what do you mean effective asymptotics? You start, in the Cauchy problem, you start with some initial conditions, yes? And then you say, what happens to it after a long time? Yeah? And the answer is, you can give very, very precise information, what happens. And the same thing now, we can do it using the same machinery. So this is what happens to initial conditions for the half-line problem. And there's some nice results about the small dispersion limit. Remember, this started with the old work of Lax. What happens if you take the limit of the highest derivative to go to 0? You see, you want to understand the analog of the shock. You see, remember, for the Burgers equation, how do you smooth? You smooth in terms of this usual shock wave smoothing. But when you have dispersion, you smooth through oscillations, yes? So this is the zero dispersion limit, so you can do all this from this equation. So now, let me tell you something from everything I say now. This is the newest result. Okay, in terms of numerics, by the way, in terms of numerics, this machinery also gives you some way to control the Dirichlet to Neumann map without solving the equation. You see? And this person used this as a numerical scheme, this formula. Okay, but maybe the most interesting thing is this, and it's a good place to finish. Okay, so when this, you see, remember, in the first part of my talk, I talk about the full line and the half line. And for the, I'm sorry, for the half line and finite interval. And for the finite interval, I spoke about some surprises. Yes, the surprise is that you don't have discrete spectrum, for example, for the third order operator, that for a second order operator, it's up to you. You can have a discrete spectrum by collapsing, or you can stay on the continuous spectrum. Okay, if you think of KdV, and if you think of Ornonia Schrödinger, this explosion of results started, of course, in 1972, when Zakharov and Sabat understood that what they had found for KdV was not an accident, and there was another equation called the Ornonia Schrödinger for which you could solve the Cauchy problem. Now, once you have two, you have infinitely many. And then very early on, the great people like Peter Lax, Henry Makin, Espinovikov, etc., posed the problem of solving KdV, etc., on the finite interval, but with periodic boundary conditions, which of course is not very physical, but it's also what you numerical guys do a lot of the times, you see, because things are simpler. Yes. So can you solve, for example, KdV with X periodic boundary conditions? You see, and later on, other great people like Atiyah and Mannion, etc., generalized this to instantons and all this. And it turns out that there was a diversion at the time. So in this integrable machinery, some people work on the infinite line, some people work on the periodic. Almost there was zero intersection, except maybe it was the only person I know who worked on both, right? And I never worked on this, but I had the feeling that this problem was open. I was afraid to state it, but then last year I got a grant and I brought somebody who is an expert in this business, de Koning, and of course he confirmed that this problem, in spite of this work of these great people, was completely open. What it means completely open? You see, what they had done with these very powerful algebraic geometric techniques, so Riemann surface, etc., was the following. They had only constructed a particular class of solutions. You remember on the infinite line, the simplest localized solution is soliton, yes? But then, of course, you can have a formula for the n-soliton solution. If you go to KdV, the analog of the one soliton is a knodal wave. You can have n such knodal waves, yes? And this is the so-called n-gap solution. And you have a very beautiful algebraic geometric construction of these solutions. But, of course, if you take the solution and you evaluate it at t equals 0, you get some concrete function, q0 of x. So if I start with this very special q0 of x, I will have the solution. But suppose I don't. Suppose I start with an arbitrary. What will I get? Of course, people knew about this. They had some mild, especially for small dimensions, they had some mild completeness results that you can expand the function as a sufficiently large genus solution. But they knew that this problem was open, and there were attempts to go to the limit of infinite genus. Trubovich wrote a beautiful book of precisely on this topic, but again, this was not practical in integrable systems. So in other words, this problem remained open, you see. I already mentioned to you that this method, at least for linear problems, could do, of course, finite interval as well as half-line. And indeed, for the nonlinear problems, we wrote a paper with each when we did this. But you see, in general, for arbitrary boundary conditions, you have an additional nonlinear step in this method. But if you have a special initial conditions called linearizable, then it's as effective as before. I showed you this example of linearizable boundary conditions earlier. Come on. This, you see? For this, for example, everything is as effective as the infinite line problem. Zero difference. The only difference is that you have a Riemann problem on the cross, but so what? You see? Everything is explicit. Okay, so we understood with, we had already understood with each that the beautiful thing about this periodic problem, as far as my formalism is concerned, is that this case was linearizable. Therefore, in principle, one should solve this problem effectively. And this was finally achieved a couple of months ago. It's not even written, it's not even published yet. But the upshot is that the full periodic problem now can be solved in terms of a Riemann-Hilbert problem, which is defined on the cross, and which everything, all the spectral functions are explicitly given in terms of your only data, which is your initial condition. So with this in mind, we can for the first time talk about the unification in the nonlinear problem, at least for integrable equations. So this new method does the following. You see, of course, can solve problems on the line, but there's no advantage now. Everything, this was earlier perfectly done by the inverse scattering transform. It's only for pedagogical reasons you want to do this. The second is the surprise I just mentioned to you. And the third is, so for these three class of problems, the new method is as effective as the inverse scattering transform. And then if you give arbitrary initial and boundary conditions, then you have an additional complication. To get the spectral functions, you have to get the C that I wrote before. You have to solve a quadratically nonlinear problem, but this is now better under control. And part of what I talked about, but it's already, this book now is already too old, although it was written a couple of years ago. But some of the material I spoke is in this book. This was there was some conference, and in this conference I gave 10 lectures, and then part of the deal is you have to write a book, and this is the book I wrote for this. And actually, most of the book up to chapter here is about linear problems. Okay, thank you very much. Yes.
In all your examples, the spatial variable was one-dimensional. Is this an intrinsic restriction of your method?
No, this is of course a very good question, and for linear problems, no. You see, for nonlinear, it was much harder, and finally, it went to. Finally, I was able to go to small dimensions last year. There's a paper, Communications of Mathematical Physics, and it is mathematically very interesting because you might be aware that even if you solve the Cauchy problem for an integrable nonlinear equation in 2 dimensions, what now plays the role of what now was so essential, the Riemann-Hilbert problem, now becomes something called the bar. And then when you do boundary value problems, it's a combination of the bar with Riemann-Hilbert. It's more complicated, or if you like, more beautiful, depending on what, but it's doable.
What are the conditions at infinity for your solutions, and what are the conditions on the initial data for your case, for which all these kind of integrals in the Fourier space, that they are analytical and stuff?
No analytical. No analysis.
Because
You don't need anything. You need nothing more than, for the linear case, I mean, as I wrote the conditions I needed, something like H1 will be okay. You don't need any analyticity. You don't need, you worry that I need enough decays in order to have analyticity in K. Absolutely no. No, it's minimal conditions.
Now, my comment is about, like, in the sine transform plugging X,
yes.
you get zeros. I don't know why you're so surprised. Even in the classical heat equation, the whole line, we have the Gaussian. You cannot plug t equals to 0 to get the initial value.
No, I'm not surprised. What I'm saying is that any problem you do by initial conditions, by separation of variables, because when you derive the transform, you do it by homogeneous conditions, then of course you will have a lack of uniform convergence. But this is a problem not only how to verify the equation, but it's also a problem numerically. And then you see, if some, as I mentioned earlier, I remember one student, when I was a graduate student, I was teaching assistant, and one clever student asked me what happens. I couldn't answer, and then I tried to do it, and then I said, well, go to the complex plane, which is exactly what I did. You see, the thing is, for me, this whole business is very, very surprising, because if you go to ODs, then indeed, when we find integral representations, what we do is we are in the complex plane. Yes, all these beautiful integral representations, which are so important for asymptotics, etc., are in the complex plane. But when we did PDEs, there were, of course, some sporadic cases, like Sommerfeld contours, etc., but there was absolutely no systematic attempt to go to the complex plane. And my answer is, a complex plane gives you a huge advantage. That's the statement.
Thanks again.